So last time we did the first derivative test, we set our first derivative equal to 0, and we got, what are those called when you set first derivative? Critical points. Perfect. So let's fill in the beginning of our table where your original function is increasing. What's going on with your first derivative? Positive or above sea level. And where your original function is decreasing, first derivative is negative. So the first derivative tells us increasing, decreasing, relative maximum, relative minimum. So we get 4 things out of that. Remember, we were writing all 4 sentences and all that. Okay. Today we're going to do second derivative test. And so instead of critical points, we call them inflection points. And so you're going to set your second derivative equal to 0. Here is a subtle difference though. When you set the first derivative equal to 0, whatever you get, those are critical points, period, end of story. These are only inflection points if there's actually a change. Do you remember how I showed you the cubic graph and I said in the middle there's a critical point, but it's not a location of a maximum? It still counts though. These don't count unless there's a change. Now what the second derivative tells you about is concavity. So there has to actually be a change in concavity. And someone's always like, what are we at the dentist? Cavities? No. Concave up and concave down is what I'm talking about. It's the direction the graph bends. So concave up is like a smiley face. Concave down is like a frowny face. Okay. So are we together there? All right. So I'm going to draw you a little picture. If you have the original function, this is what a change in concavity would look like. You would have concave up like this. And then at that point, it changes to concave down. Do you see that? Like, I can't force you to see it, but do you see what I'm trying to draw for you there? Think of the sine or the cosine graph. They have tons of inflection points. Concave up, concave down, concave up, concave down. It's the way the graph bends. So that's an inflection point. If you change from concave up to something linear, that doesn't count. So if it changes to linear, it doesn't count. It has to actually be a change from concave up to concave down or vice versa. Yep, that's the inflection point. Okay. Now, if you're looking at the derivative graph, because sometimes they give you, well, oftentimes they give you the derivative graph and then ask you questions about f of x, you know, the one you're not looking at. So for f of x, you would have a change from increasing to decreasing. That would be where you'd have a point of inflection. Or from decreasing to increasing. That would be where you'd have a point of inflection. If you change from increasing to constant, that doesn't count. The constant part won't count as a change. And several years ago, they put a derivative graph on the free response part, and it had all these little constant segments on it, and it asked for the inflection points. I guarantee you my students put all of them. None of those counted. They're evil. Okay. And so I have started doing that in my notes now, like trying to really stress that part doesn't count. There has to actually be a change. Okay. I know I just lectured about that for longer than I probably needed to, but I did that because it came up one year and I know people probably missed. All right. So now we can go and fill in the rest of our chart. So if this information is true from the original function to the first derivative, it's true from the first derivative to the second derivative. So you can copy this stuff over. Again, increasing, positive, decreasing, negative. And in theory, it would be true as many derivatives you want to take. There's no third derivative test. Okay, after this, we'll be done with it. All right, but if it's true from here to here, it's true from here to here. And then the other thing we can fill in, where your second derivative is positive, that tells you about the concavity for your original graph. It is concave up. And CCU is a standard abbreviation for that. Concave up. Second derivative is negative, means concave down. We don't get anything for this part of the table. I usually just leave it blank. If you want to put X's through there, I guess you can. But we don't have any information that's going to go in that part. All right, so here is your second derivative test. If you have a critical point, if C is a critical point, so you've already done the first derivative test and found your critical points. If your second derivative is positive, We just said that means concave up. It will look like this, like a smiley face. That means that critical point right here is the location of a relative what? Minimum. Relative minimum. I just always draw the little U shape so I can visually see it. Second derivative is negative, less than 0. That means concave down. It would look like this. That means your critical point gives you a relative maximum. Very good. I like things that are visual that you can see. I think that's why I like trigonometry so much, because you can draw a triangle. I'm like, okay, 3 sides, 3 angles. I can deal with that. I know you guys don't all love trig, but I do. All right, and if your second derivative equals 0, there's no conclusion. You can't conclude anything if you don't have any concavity there, if it is an inflection. So we are going to go through the entire process with one of these. Won't take as long as you think, all right? Find the critical points. That means you're going to do what? Yeah, first derivative, set it equal to 0. Now again, and I brought this up last time, you can't use pronouns like they or it, because you have a f, an f prime, and now an f double prime. So you have to, you know, label who you're talking about, all right? So first derivative equals, that would be 3x squared plus 6x minus 9. I want to set that equal to 0. They'll all divide by 3. And then that's going to split into what? And so your critical points are x equals -3 and x equals 1. This is a review of what we did last time. Intervals of increasing and decreasing. You're going to make number lines for each of these factors. So a number line for your x plus 3, number line for your x minus 1. And so if nothing weird or backwards happened, it's going to be negative and then turn positive. You can slice up your number line. And what's your overall sign for the first section? Positive, and then negative, and then positive. And we're going to write 2 sentences. How did I say the sentence should start? What's the subject of your sentence? Yeah, so it's f of x is, it's one or the other. So just think about like how you want to phrase it. F of x is increasing, where? Negative infinity to -3. Union 1 to infinity, because, and who's your source that you're citing? F prime. It's the first derivative test. So because F prime is what? There we go. I just drill the sentences. I just drill them and drill them and drill them. On the AP exam, that's the answer. I can't change the answer because it's a definition. Do you remember we were talking about that with related rates and it was a cone and I was like, this is the volume of a cone. I cannot change that. Same thing with this. All right, here's your sibling sentence. F of x is what? Decreasing everywhere else for the opposite reason, right? -3 to 1, because f prime is negative there. C is going to be the other, well, I won't make you write the whole sentence this time. We'll say it verbally. At which one of these numbers are you going to have a relative maximum? The -3 or the 1? Which one gives you is the location of relative maximum? Good. So we're going to say relative maximum at x equals -3. I won't make you write it, but let's do it verbally. Because, who's your source? F prime changes from positive to negative there. Good. And then we're going to say relative minimum at x equals 1. What's the justification? Because f prime changes from negative to positive there. Good. All right. Oh, do you remember how we do absolute? This was on the other side of the notes when we flipped it over. Do you remember what the test is called? for the absolute ones on an interval. Candidates test. Who are your candidates? Good, and those are called, those are endpoints. And then who are your other candidates? Endpoints and critical points. All right, so our endpoints are -4 and 0. What are our critical points? -3 and 1. Now I'm only going to use -3. Why wouldn't I use 1? It's a critical point outside of the interval. Where do I plug those into? Good, perfect. Okay, good. Plug them into the, now sometimes you have to battle here. They don't give you a calculator a lot of the time, and you got to fight your way through it. So we're going to plug -4 back in all the way up here. -4 cubed, -64. All right, -4 squared would be 16 times 3 is 48. -4 times -9 is 36, and then +4. So let's see. 36 and 4 is 40. Plus 48 would be 88 minus 64, 24. Good job. Nice. All right, let's do the same thing with -3. Again, sometimes you got to fight your way through it. -3 cubed. All right, -27. -3 squared would be 9 times 3 is 20. That's kind of nice. -9 times -3 is 27 plus 4. All right, so these cancel. 27 plus 4 is 31. And then if you plug in 0, you just get 4. Perfect. Now always write it the same way. Absolute maximum is, what's the biggest number? 31 at x equals -3. Good. And then absolute minimum is 4 at x equals 0. Sometimes they ask you for the maximum or minimum. Sometimes they ask you for the location. If you write it that way every time, you'll get the whole thing. And we did not write because, but we still justified what counts as your justification. Your table is the justification. Go ahead. Yes, you can write ABS for absolute and REL for relative. Those are all good. All right, that was a review from last time. Now we're venturing on into the second derivative. How would you get your inflection points? Second derivative, good, equals 0. Okay, so go back to your first derivative in part A. So we're looking back right here. The derivative of this would give you what? 6x plus 6, good, equals 0. And then you would solve that. Now that's only an inflection point if there is a change. It doesn't count if there's not a change. So you're going to take your second derivative, this 6x plus 6, and make your number line. Doesn't count unless there's a change. There will be, though. The only time there's not a change is if there's a squared. Do you remember why? If you square something, it's always positive, and so there's not a change. So there will be a change. It's going to be negative and then turn positive. But again, I'm just bringing it up because they do that sometimes. Like you'll solve it and get an answer and think, woohoo, that's my answer. But if there's not a change, it's not an answer. Okay. And then intervals where f of x is concave up and concave down. It should start the same way. F of x is or f of x has, all right? So it's going to be f of x is concave up. Where do you think? Yep, -1 to infinity, good. Because now who's your source? Who are you citing this time? Who are you quoting? Double prime, second derivative, because second derivative is positive there. So you have to make sure you cite the correct person. It's like you're talking about f of x behind their back. It's like f double prime is spreading gossip about f of x. Like this is your source you're citing. All right, and then your sibling sentence. F of x is concave down. Yeah, everywhere else for the opposite reason. So because second derivative is negative then. we'll do our little break and then we'll keep going.
How did you find which one you use? This one, I don't know.
All right, I'm gonna pick and choose because some of these end up sort of similar. This one's really similar to the one that's on the back and I like that one better. So I'm gonna skip this. I'll fill in anything we don't do. I knew there were gonna be like more problems on here than we needed though. So let's go ahead and go to number 3. So this time, instead of being given an equation that you actually find the first derivative and second derivative, all the information is given to you in a table. I kind of like that. You don't have to actually do any math, so you can't make like a negative sign error or anything, like you can't make a copy error. All those go out the window. Everything you need is right here, so it's kind of nice. All right, let's do the graph first. Let's graph it first, and then we'll go and use our graph to answer all of these. The points that you can put on your graph are the f points. We're going to graph f of x. So your first point is going to be 0, 0. Can you pull out from the table like another point? Yeah, 1, -2. That'll be right there. 2, 0. And then what else? 3, 3. All right, so you're just pulling those from the table. Now, you don't really need to look at the first derivative, and here's why. The first derivative tells you increasing and decreasing. That's just going to happen when you connect the dots. You can't get from here to here without decreasing and from here to here without increasing. Do you see what I'm saying? It's going to just happen, all right? You really just need to look at the second derivative. That tells you your concavity. That's which way to bend the graph. So for the first little section there, from 0 to 1, x is 0 to 1. It says your second derivative is positive. That means you want to be concave up. So when you connect those first 2 points, just try to bend it so that it would be like a smiley face. You're just bending it the correct way. Do you guys know what concave and convex means? Like a contact lens? If you don't, that's fine. It's just the way things bend. I bring that up in case you know what that means and that helps you understand it better. All right, from 1 to 2, it says your second derivative is positive. So connecting the next 2 points, you still want to be concave up. So like a smiley face. And then from 2 to 3, it says our second derivative is positive. So you still want to be concave up like a smiley face. So something like that. Now to like make the connection here, at 2, there is a what? Sharp edge. Look at your table. At 2, you can't get it, not differentiable due to sharp edge. You're making the connection that like it should make sense, okay? Then you can use this graph to answer all the questions. Find the absolute maximum. Well, what's the highest point? Yeah, 3, 3. So it would be 3 at x equals 3. The absolute minimum, that is the lowest point. Yeah, -2 at what location? At x equals 1. Now, relative, they could be the same as the absolute. They can't be endpoints. Relative cannot be an endpoint because an endpoint is not relative to something on the other side. Also, you could have more than one of them, like if the graph turns around a bunch of times. This one kind of doesn't, though. Do we have a relative maximum? Like the graph goes up and comes back down? No, it just doesn't do that, so none. Relative minimum means it goes down and comes back up. Yeah, it's the same as the absolute minimum, which is fine. They can be the same thing. And then this one's actually kind of tricky. I'm going to throw it out there and see if anyone gets it. Inflection points. Why are there none? It doesn't ever change. It's concave up all the time. It's positive, positive, positive. It never changes. The second derivative, I shouldn't say it, never changes to negative. There's never a change, so there aren't any inflection points. Interesting. All right, let's try 4. Here, we're going to sketch a graph. Sketch a graph with the following characteristics. Oh, you know what this reminds me of? Do you remember a million years ago when we played Taboo? You had to draw the graphs, kind of like that. All right, vertical asymptote at x equals 1. So go ahead and dot that in. This is like your art skills here, doodling in math class. Horizontal asymptote at y equals 2. Now you can dot it the whole way across if you want, but if you were with me in pre-calc, I always stress this. It's just the edges. It's just the end. In the middle, it could go through. It's not going to, but it could, right? Now this is first derivative is what? Negative. If your first derivative is negative, what is your, look at your sticky note. If your first derivative is negative, what is f of x doing? Good, decreasing. We want to decrease for everything smaller than 1. That's this portion here. So you're gonna have to coast along the asymptotes and make it be decreasing. It can be wherever you want it to be though, because they didn't give us specific points to go through. All right, then what does this mean? First derivative is positive. That means your graph should be increasing. So number 5 is almost the exact same as number 1, and I have one like that on the quiz review that we're going to do, so I'm going to skip that one because we're just going to do that over and over again. Oh, it's all the same thing, but we are going to do number 6 at the bottom there. All right, I like these because you really don't have to do much, but you have to understand the calculus, so I do like it. All right, it says a differentiable function, oh sorry, it should just be function, has the following things that are true. F of 3 equals 7. All that's telling you is the point 37 is on the graph. That's all that is. That's not really giving you much information. It says the derivative, first derivative at 3 is 0. What does that mean? Because that now gives us something. It is a what? It is a critical point. You would have, I think what you were thinking of, and you're right too, is the horizontal slope. Because that's what that means. It means at that point, you have a 0 slope. Is that like what you're thinking? That's correct too. Critical point though, is what we're looking for. Critical point, and that's what it would look like. And then this says the second derivative is -4. Now, I think what gets people on this is the fact that it's -4. It doesn't matter that it's -4. It's important is that it's negative. Look at your sticky note. If your second derivative is negative, that means it is concave down. So if your graph is concave down and you have a critical point, it means that, oh, I already sort of drew it. It means that critical point is the location of a what? Okay, you guys got it. Nice job. Perfect. But it's the fact that it's 4 that hangs people up. It could be -3 or -17 million. It's the fact that it's negative, means concave down. So don't get hung up on the numbers. All right, we'll try some of these back here and then I'll give you the quiz review. They love to give you the first derivative graph. Be aware of what they gave you. I really stressed that when we did velocity and acceleration. I was like, what did they give you? What did they give you? Usually they give you the first derivative. Okay, so let's look at 7. Look, you're going to rely heavily on that sticky note right now. On what intervals is f of x? Not the graph you're looking at. Not the one you're looking at, okay? Increasing. Look at your sticky note. Where f is increasing, what should first derivative be doing? That means above sea level. That's where the graph you are looking at is above sea level. So where is that happening? Yeah, now this starts at -8 and ends at -10. So we won't have any infinities on it. Like I should have stressed that first, but yeah. So -8 to -6, good. Union. Now you don't have to stop at 4 because the first derivative stays positive there. So all the way until 9.5. Beautiful. Decreasing is where your first derivative is negative. That means below sea level. That's going to be everywhere else. So -6 to -2, union 9.5 to 10. Now I'm going to have us look back at our sticky note. Concave up is where the first derivative, we know it's where the second derivative is positive, but you don't have the second derivative. You have the first derivative. Look at your sticky note. Concave upwards is where the first derivative is what? Perfect. Good. Where is this graph increasing? From where to where is what we want to put. -4 all the way to 2. Good. -4 to 2. Union, where else is this graph that we're looking at increasing? 4 to 7. Good. Concave down is where the first derivative is decreasing. That's going to be everywhere else. Okay, so that'll be -8 to -4. Union, what else? Yeah, 2 to 4, union 7 to 10. You unfortunately can't write everywhere else. All right, number 8, local, that means relative maximums. That is where the first derivative changes from what to what? Maximum. Positive to negative, that is above sea level to below sea level, above to below. Where does this graph change from above to below? -6, and there's one other one. Perfect. -6 and 9.5. Local or relative minimum would be where the first derivative changes from what to what. Okay, so that's below to above, -2. Extension question. Where is there a critical point, but you don't end up with a relative max or min? Perfect, good, 4. All right, and then inflection points, look at your sticky note. It's where the first, or no, I'm sorry. It's where the original function changes from concave up to concave down or vice versa. So that's where the first derivative changes from what to what. Good, increasing to decreasing or decreasing to increasing. There's going to be a lot of them, okay? Where do we have a change from decreasing to increasing or vice versa? All right, -4. What else? 2, good. You did not get hung up by the -1. Very good. 2, what else? 4, and one more, 7. Good. Why is -1 not? Yeah, that part's still, and it's still increasing. You don't have a change to decreasing. That doesn't count, okay? What time do we go to lunch? We're gonna use these as a warm-up for next time because I like these questions and I don't want to skip them, but I want you to have time for the quiz review. So hold on to that. We'll do that as a warm-up for next time.